Okay, then. Maybe I will. Maybe we'll go live. Maybe that's what's going to happen.
It does not know.
So released an episode of The Guide to Space yesterday, and there was just the happiest Robin singing his little heart out while I was doing the episode, and it's just like so loud. There's no removing it. There's no compensating for it. It's just a Robin. Just yeah. So
I get chickadees when I Twitch stream Saturday afternoons.
chickadee. Yep.
Yep. Very happy to be alive, chickadees. I learned this morning because of my dog that the chickadees wake up an hour before sunrise.
Chickadees are. People want to see your T-shirt.
Oh, that's what. Okay, hold on.
It's like it's a Star Wars symbol, but it's a rainbow flag. Right on.
I couldn't hear. I have no idea what you just said.
Oh, I said it's a Star Wars symbol and it's a rainbow flag.
Yes, may the force be with you. And the fourth.
Oh, it is the fourth. Oh, well. I'm not. I don't observe May the 4th. Now, if they want to make a Star Trek day, sure, but what would that be?
Well,
Leonard
so
Nimoy's
it's always
birthday?
live long and prosper, and I don't know what date you would prosper upon.
Yeah.
Internets, you need to solve
this one. Yeah, we got to have all denominations be able to celebrate, or maybe a Stargate Day. That would be all right. Expanse Day.
I don't know.
I'm going to say hi to some people. I'm going to say hi to Abraham Cottrell, Adam Synergy, Arnold Post, Ben Kalo, Coffee Singularity. Whoa, the Coffee Singularity. Can you imagine that? Colin
I think
Jones.
I'd be very good friends.
Douglas Crandall, Esther Gagne, Ghost World, Gordon Dewis, Graham W., Guido Bibra, Harry M., Helg Bjorkog, Holly Meyer, Israel Palanayuke, John Seffil, Kira Heiler. Sorry, the first time I got to go slow. Lars Ray Jepsen, Linda Sadik, May Vision, Michael Meyer, Mr. Tom Harbin, Nicholas B., Noel Ruppenthal, Paranor 001, Paul Smith, Peter Quinn, Rinstro, Rick Schwartz, Arjone, Side MT, Thomas Traniker, Umu, Uncle Bill Druin, and Zapvan. Hey, everybody. And Phoenix is saying hi from the Slack chat, so, you know.
Hi,
hey,
Phoenix. Phoenix is a good buddy and is going to see the Insight launch, and I am terribly jealous.
Sondi and
Morgan?
And Morgan, and who else is going to be there? I'm sure the West Coast peeps are going to all be all over this. Yeah. I'm sad I'm not seeing this one. There you go. Can't be everywhere at all times. So if you're wondering what it is that you have stumbled into, this is going to be a live episode of Astronomy Cast. I'm Fraser. That's Pamela. We're going to take about half an hour to do a show, and when we're done, we will stick around and we will answer your burning questions about space and or astronomy.
This is what we do.
This is what we do. This is all we do. We absolutely will not stop until they're answered. All right. Does anybody have any reason why we should not begin this show? Forever hold your peace.
I am ready to enter into this recording.
Let's do it. Let's record it. I'm ready to
press
record.
Pressed record. Hello, Chad.
Whoa. It's going to be like stereo when he listens to that. All right, let's begin with the intro. What?
Chad, I apologize for the leaf blower in the background.
I can't hear it, so he won't be able to hear it.
The audio can hear it.
Oh, okay.
It's really high pitched, so you should be able to filter it out.
Here we go. Astronomy Cast, episode 490, Supernova update. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, the Director of Technology, Citizen Science at the Astronomical Society of the Pacific, and the Director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. May the 4th be with you.
That's when we're recording. And as we mentioned, I don't observe May the 4th. I need a special Star Trek day for me and like-minded individuals. So if anyone knows what day that should be, that would be great. Time for another update. This week, we're going to look at what's new with Supernova. And once again, we've got good news. Lots of new stuff to report. Now, before we even start, the one big update that has not happened is we have not had a close, bright supernova since 1987.
This is true.
Another decade has gone by, and that wasn't even in our own galaxy.
I know. And so here's the thing, guys. There is statistically supposed to be a supernova on average every 100 years in every galaxy like ours. And we haven't had one in like way more than 100 years. And so the question is, are they on the other side of the galactic nucleus, buried in gas and dust? Is our galaxy going, nah, you're not allowed to have one, which is my personal belief. Or are we just going to like catch up by the rule of averages and have like 6 all at once?
Right. Now, I've heard they happen maybe even more often than that, but there is a big chunk of the galaxy that we can't actually see. So it could very well be that our supernova went off and we didn't see it thanks to the stupid galaxy in the way.
Yeah, this is true. This is sad. The best hope is maybe we'll get better at watching them maybe with neutrino detectors. We have detected some gamma ray bursts with neutrino detectors. I think there's been a few supernovae that have been seen this way. So maybe as we get better at pinpointing what direction supernova stuff comes from, maybe if we get unlucky, well, lucky because they'd be far away, in the direction that GRBs come from, if we have a GRB in our galaxy, we could see it just in other wavelengths of light, in other kinds of detections like neutrinos, which is a particle instead of light. But yeah, bad times if you're a supernova explorer who wants to study the individual chemical components, which is what we use nearby supernovae for.
Yeah. Well, but I mean, there have been a lot of supernovae. Stars are exploding across the entire universe all the time, and fortunately, they're bright enough that we get a chance to see it, even though it's so distant. What new and interesting things have we learned since we first covered supernovae? I'm not sure when, but I'm sure it was right at the beginning, because again, we were going after all the low-hanging fruit. So what have we learned?
Well, one of the biggest and kind of frustrating things that we've learned is, last time we talked about this, I talked about how we generally use type 1a supernovae as standard candles. We assume that all of them are at the exact same luminosity. This means if you're a type 1a supernova, you start with this amount of material, you go kaboom because of degeneracy pressure and things like that, which would be an entire episode. We did one.
Yeah.
And because you're going kaboom with the exact same mass of fuel, basically, and it's that basically that gets us in trouble, every single time, same size detonation, same size explosion, same amount of light given off, standard candle.
But, okay, so before you go deeper down this rabbit hole, I just want to give people the quick, for when you said, type 1a supernova and just went on. They're all the same. Just can you give a brief explanation of what is these orbital mechanics? What makes that type 1 supernova go off with roughly the same energy every time?
So you have, and I'm looking for props on my desk because that's a thing I do. I have a red giant star. I am now looking for a white dwarf.
Podcast listeners, I apologize.
Okay. Okay, so I'm going to use...
I will try to explain what Pamela is going to be doing here.
So you have an itty-bitty little tiny star called a white dwarf that is roughly the size of the Earth's moon. And it is orbiting nearby a regular everyday star. It could be a red giant. It could be a main sequence star. It could be any kind of everyday star. And our white dwarf star has so much gravity and is so tiny that it's able to snuggle up right next to our everyday kind of star. And as it snuggles up really close, its gravity's like, I'm going to nom, 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 nom on that supergiant, on that main sequence, on whatever that companion star is, it gets eaten. And in the process of consuming its partner through a process referred to as stellar cannibalism, the white dwarf gets more massive and more massive and more massive. And as this occurs, the protons inside of it, the atomic nuclei inside of it, because these are either they're a mix of hydrogen, helium, and carbon. Different stars have different dominant atoms. Doesn't matter. As it gets more massive, the gravity trying to collapse it eventually overwhelms the force of all the little protons going, don't come near me, which is the electromagnetic force. And when that electromagnetic force gets overrun, when the electron degeneracy pressure of all the electrons going, don't come near me, when that gets overrun, it tries to collapse. And depending on the situation, how we see it can vary, but whatever happens, it should give off the exact same amount of light as it goes kaboom. Now, it gives off the exact same amount of light. We see different light curves. The difference in how we see it is how quickly we catch it. Sometimes we catch it during the brightening phase, which is awesome. More science occurs. Sometimes we catch it during the downside of this brightening and fading. And we're sad because we don't know what its maximum brightness was. And that's what we use for research. But wherever we catch it in this brightening and fading, it is always the explosion of basically the exact same mass, because that's the mass at which the protons and the electrons are like, dude, I can't support you anymore against gravity.
All right. And so now the problem is that we found out that it's not always exactly the same mass.
Well, it's not so much that it's not always the exact same mass as it's not always the exact same brightness, which is worse. So the theory was you're exploding the same mass. It should go kaboom with the same luminosity. But it turns out, just like if you're looking at a 100-watt red light bulb versus a 100-watt blue light bulb, they do not seem to illuminate your room the same way. If you have a explosion that has more stuff that isn't hydrogen and helium in it, you start adding in carbon, you start adding in iron, you start adding in titanium, you start adding in the entire rest of the periodic table that is not hydrogen and helium. And that change in content, which astronomers, because we're lazy, refer to metallicity, and hydrogen is X, helium is Y, and everything else on the periodic table is Z. If you increase that Z value, it turns out that it looks like the supernovae are dimmer. Yeah, which means not standard candles, which means as we look back in time and the amount of that Z, that amount of that metals that has had a chance to form goes down, which means how supernovae that we use as standard candles to measure the expansion rate of the universe, how they behave, changes with distance. Luckily, we have measured the acceleration of the universe's expansion through multiple methods, so we're good.
Right.
That's still there. But now we're confused about this one specific, very specific kind of supernova.
But can you, I guess, observe more of them, use other standard candles to double check the distances, and once you look at the chemical signature of the supernova, can that give you a better sense of how bright, inherently bright it was? Is there a way to get back to a really nice standard candle with the Type 1a supernova, or is that measurement tool worthless?
Well, it's not that the measurement tool is worthless. It's that we need more local supernovae that come from different pockets of metallicity. We can only really measure the distance to a supernova precisely for nearby supernovae that are in galaxies that have other standard candles. So they have to have the Cepheid variable stars that we've talked about so much. They have to have as a secondary deterministic certain stars when they die, they poof off their outer atmospheres as planetary nebula. We can sort of use that as a standard candle. We can sort of use, and by sort of, I mean more error. We can sort of use some old red stars like Myra variables as standard candles. So we have all of these high error standard candles, but we really need those high accuracy Cepheids in the same galaxy as the supernova. And as you said, things aren't exploding a lot nearby.
Right. And that's the problem. If you're looking for a thing that happens 1 in 100 billion times, once in 100 billion, you have to wait a long time.
Well, and the other problem is volume. When we look out, we see this little tiny sphere of stuff that's nearby. Now, if I double the size of that sphere, I have done way more than double the volume, because the volume goes as the cube. And so as we look further and further out, we're looking at enormous volumes of space. And as the volume that we're looking at goes up and up and up, there's a higher chance of seeing these things. Unfortunately, it's a higher chance of seeing them in places that we can't see the Cepheids.
All right. So that is a downer.
Annoying.
Yeah, but it feels like the kind of thing that, new surveys, things like the Large Synoptic Survey telescope is going to find a lot more supernovae and is going to just dump mountains more data back into the hands of astronomers. And who knows, we may come back around with a much more accurate yardstick and learned a lot about stars at the same time. What else is new about supernovae? Because I've got one.
Okay, what one do you have?
We've seen 2 neutron stars collide with each other and
kilinovae.
Yeah, kilonova, and turn into but I guess it's not quite a supernova, but it's a
kilonova.
It's one of the methods that have been theorized was a gamma ray burst. And now we've actually seen this and detected, obviously, in both the gravitational waves and in the visible light spectrum, which is huge. And I think the most interesting thing is the elements that they saw formed in that collision. And that has implications for supernovae.
What is super cool is this was a GRB discovery of 2 colliding neutron stars. And my wedding ring, the thing that I'm wearing because I got married, is made out of white gold and stones. And it turns out that this particular ring, all of the atoms in it that aren't strengtheners, so all of the atoms in it that are actually gold atoms, came, we think, from kilonova explosions, where you have 2 neutron stars merging into one object. We have this massive, all of space ripples with a gravity wave. We have this ripple moving through space and massive amounts of nuclear fusion going on. And that nuclear fusion has one of its end products, gold. And we didn't know this for sure before.
Well, and that's the thing. Like, if we had this show, and you have probably, if you go back to previous shows, you've heard us have this conversation many times. Where did the heavier elements come from? And your answer would have been supernovae, core collapse supernovae. And now the possibility is that some, or maybe even all of it, comes from colliding neutron stars, and some or none of it comes from these core collapse supernovae. So that's huge.
And so just to back up, supernovae come in many formats. We have the small dense object like a white dwarf, I lost my pencil, like a white dwarf next to a star. The white dwarf eats the star, goes kablooey. We have, I'm not going to keep looking for props on my desk. We have neutron stars that eat things off of there, colleague. We have black holes that eat things off their colleagues. There's lots of cannibalism going on in the universe. We have the collision of neutron stars with white dwarfs or black holes. We have the collisions of neutron stars with neutron stars. We have the collisions of black holes with black holes. I don't know if that technically goes supernova, but it certainly creates gravitational waves. Now, in addition to that, we have massive stars that don't need to eat anything. They are happy to explode on their own, because when they stop generating enough light in their core, it turns out stars are supported by light. Right now, if you're in a room where light is shining on you, sunlight, lamplight, fluorescent lights, all of those photons are actually exerting a pressure on your body that's so small you can't notice it. Now, the Planetary Society, they've launched light sails and they've been able to maneuver spacecraft using the light from the sun. Now, with supernovae, what happens is you have a star that is supporting itself by generating photons, generating light in its core. And the outer atmosphere of the star is going, okay, I would like to collapse in and visit the core, but photons are holding me up. I'm good up here. Now, when the nuclear reactions end in that core, those photons stop going out, and the atmosphere of the star is like, oh, expletive, collapse. And during that collapse, all sorts of nuclear reactions occur because you have all these atoms smashing into one another, very short time periods. And it's that nuclear reaction caused by core collapse, the word you used, of these giant stars that also produce a lot of heavy elements, and this massive shock wave of light moving out from all these nuclear reactions that get triggered during the collapse process.
So that's a thing we learned. What else have we learned about supernovae?
That some of them are just plain weirdos.
Like weirder than a star with many times the mass of our sun exploding inward at a significant portion of the speed of light and releasing more energy than potentially the rest of their galaxy combined, spewing heavy elements out into space. Weirder than that?
Yes.
Okay. Tell me how. Explain how.
So every family has to have that weird uncle, that weird cousin, that weird aunt. We've all got them, and it turns out even supernovae families have them as well.
If you don't, is it you?
Yes.
Yeah, all right. So the weird uncle of supernovae.
So there was a supernova that was observed, and everyone measured it. It was about 50 years ago. That's a thing. They've been going off. They've been studied for thousands of years. We can actually use ancient Chinese records to find out when different supernova remnants that we see in the sky were formed. So there's a record of one going off 50 years ago. And then along comes the Las Cambras Observatory, which is doing an amazing survey. They pick up supernovae on a regular basis. They also pick up asteroids, comets, all sorts of cool stuff. And a grad student, because it's always a grad student, was going through the latest data, picked up what looked to be a supernova, and it was the same object.
Okay.
So it appears that we can have these objects that periodically go off, but don't completely explode. They just think about exploding. We think they're a supernova. Turns out we're wrong, and they surprise us later by finishing the job.
Wow.
Yeah.
And so, but did it finish the job on the second go around, or?
We think so. We think so. Now what's cool is this is basically the exact same thing that Eta Carina is going through. Well, not the exact same thing. It's very similar
right,
to the process.
Right, because it flared up
a
while ago.
So the way stars are named is in general, but not always. The first brightest star, the most bright star according to human eyeballs in a given constellation is Alpha. Next one's Beta, next one's Gamma. Keep going through the Greek alphabet, which means Eta Carina, which is the brightest star in Carina, was not the brightest star by a few stars when it was named. For a while, it was the brightest star in the entire sky. And then it faded away. And it has flared up periodically, and it is one of the coolest objects and one of the ones most likely to go supernova in the southern skies.
All right, I've got another one for you that's new and weird.
Okay.
There's another class of supernova that have turned up, and they're failed supernova. Have you looked into these at all? They're also called
Yeah.
unnova.
I didn't know that
That's the
part.
term,
That's
unnovae. Yeah,
awesome.
yeah. And so the gist is like often they're like red supergiant stars, and they give all the indications of going through the first stages of a supernova, but then they fail. And what it looks like is the inward pressure and that sort of need to turn into a black hole, just instead of them blasting out all that material, they just completely implode and just disappear.
That's awesome.
It's totally crazy. Yeah, there's only been a couple of them have been found so far um, within the last 10 years, but still, it's sort of this really interesting potential path that some of the big stars. And so there may be more supernova out there that we just don't see because they just go and they're gone, which I think is just amazing.
That is cool. That is very cool. I I did not know that name.
Unnovae. Yeah.
I'm going to be laughing about that for
Yeah.
a long time. That is the one time astronomers could be trusted to name something well.
Properly. Yeah, exactly.
Okay, so did you hear we finally found a survivor from a supernova
That was
explosion?
like just a couple of weeks ago. Yeah, that's
Yeah.
amazing.
So when we do these update shows, sometimes the updates were like yesterday or last week. It because science is constantly evolving. The reason we do science is not because we know everything. It's because we want to know everything and we don't yet. So we keep looking and we keep finding new stuff. And in this case, supernova 2001 IG, which tells us when it was found. Those letters correspond to which half of which month and which one in that half of the month. So back in 2001, there was a supernova that went off about 40 million years ago in a galaxy named NGC for New General Catalog, even though it was started over 100 years ago. NGC 7424, bad name, cool object. So this particular galaxy had the supernova go off, and over time the brightness from the supernova fades. The gas dust shock wave that's pushing through space around it expands, and as it expanded, Hubble went back to look to see what it could see, and it found this little survivor going, "Hi, I'm still here. I wasn't eaten." And that's just kind of cool. Like, we've theorized that there are
Hmm.
supernovae, core collapse supernovae in binary systems. And this is the first time that we have evidence of this. Yes, we were right.
Well, and the super fascinating part about this is that the supernova went off and it plastered the companion star with material. And so they're able to study the companion star and look at the elements that are in the companion star and get a sense for what was in the other star as well. So it's, it's sort of like, it's a kind of it's a really amazing discovery and the kinds of things that astronomers have been really hoping to see for a long time.
And so now the question is becoming, can we get better at going back now that we have all of these amazing surveys? Sloan Digital Sky Survey, Gaia, oh my gosh. I think it's safe to say we are both in love with Gaia.
Mm-hmm.
Go back, listen to the episode if you hadn't. It's an amazing technological marvel of data production. That word.
We haven't done an episode on Gaia, have we?
Yeah, no, we did one on it when we were talking about all the big survey missions that were coming up.
Yeah, but we didn't like specifically. Yes, we did.
Yeah.
365. Never mind. We did it.
So with all of these surveys, we're going to have the ability, and this is new, or at least new since the Sloan Digital Sky Survey, really, to go back and see image after image after image of the same fields taken with the same high quality detectors that aren't glass plates, because we used to have to go crawling through Harvard to find this stuff in their glass plate library. we're going to go be able to go through all of this digital material and go, I found a supernova. I'm going to find its progenitor.
Yes.
And this ability to match thing that exploded with thing that was going to explode before it exploded. This is going to open the door to so much new understanding.
And that's there are so many of these surveys, as you said, and I'll do another callback to the Large Synoptic Survey Telescope, which is going to be, it's going to find so much material in the night sky. But even as, things like Gaia, even things like TESS are going to potentially turn up some of these objects. So the more just surveys that are going on all the time, the more of this kind of material we're going to start picking up. And it's funny how I think astronomy is going to be less and less about picking some target and observing it very carefully, and more about crawling through these gigantic databases to come up with insights. So,
and as a database programmer, I am so happy about this. This is my kind of science. So I'm stupidly pleased with the direction that we're going in.
Yeah. Have you got any more interesting supernova news?
I think we hit all the key big changes to the field, and I'm hoping Adam Reese will force us to do another update in a year or so as we figure out what's wrong, as we talked about before, with calculating H0 in the local universe versus using the early universe. But we'll be here recording Astronomy Cast when we find the answers.
That sounds great. All right, thanks, Pamela.
Thank you, Fraser. Now, don't go anywhere. We're saving. And then we'll be back to answer your questions. Except I have to press stop first.
I'm just going to save. This is for, 4 million. What is this? 490.
Thank you.
Yeah, you have happy birds now.
I have happy birds. They're going to get louder and louder as the day goes on.
What is that?
They're loud in the morning. The cha-cha-cha-cha-cha-cha.
Yeah.
That's a cardinal.
Okay. Yeah, we don't have those. Our version.
They're very, very pretty. They're very angry by nature.
Our version of that is a Stellar's Jay. And same deal. Just loud, boisterous, tons of personality. Yeah. All right. I've saved. So there was a question here. Quadlibet, who I didn't get a chance to say hi. Hi. What about those huge supernovae that don't even leave a black hole behind? Can you say a bit more about them? What actually happens there, and where do those heavy elements go? Well, I think we know. They don't leave. So these are the ones that are so big they just kaboom, and there's nothing
Kabloom.
left. Yeah, nothing left behind.
Well, there are a variety of possible leftovers from supernovae. In some cases, we get pulsars, which are little tiny neutron stars with a tangled up magnetic field that, as they spin, pulse light towards us, thus calling them pulsars because we're unimaginative. Then you also have the ones that go kablooey and leave behind a black hole. Can't tell you what's inside of those because can't see it. Then we also have those that simply go away. And in this case, the nuclear reaction's basically complete. You have a shock wave that scatters everything that's continuing to try and come in. And this is the key. You have core collapse. As it starts trying to collapse, nuclear reactions are going off. So suddenly you have explosions. And we've all seen on TV, and we know because of TV, that explosions make things go flying violently.
Right.
Now, while actual reality on Earth doesn't fly as violently as movie explosions, supernovae have nuclear reactions going off during collapse. And these nuclear reactions create massive shock waves, force of light pressure going out, and this disrupts the infall process, and you end up through all of these madcapped reactions blowing things to smithereens and creating a massive shock wave that pushes out everything that was trying to collapse in.
And I think we talked a bit about this last week, that this is why you don't get black holes beyond a certain size for the stellar mass versions, because if the star was too big, when you get to the Eta Carinas and the things that are 50, 60...
bigger than Eta, probably.
Well, isn't it in the the
It's right on the boundary. We don't
60.
know how much mass loss it's
Yeah,
going to
yeah,
keep
but like
having.
100 times the mass of the
Yeah.
sun, 150 times
Yeah.
the mass of the sun, like for those really big ones. And then the other possibility is back at the beginning of the universe when you had those original stars with the just the primordial hydrogen and helium. They had the potential to get much larger, and I think they had the potential, depending on how they came together, to go kablooey fully in some cases. So
It all comes down to we just don't understand mass loss. So even our sun, and this is why there's been such amazing northern lights for people who are still far enough north to have long nights, or south. South is now the optimal place to be to see aurora australis. Um, our sun is giving off mass. All stars are giving off mass. We're not entirely sure of the rate. If they lose too much mass, they're going to have too little mass to have the most exciting of supernovae or gamma ray bursts, which are probably hypernovae. There's lots of ways things can die.
right.
And thus goes the end of life.
All right, hit us with some questions.
I looked at the chat and they almost made me die laughing. Esther Gangney,
Yep.
I think I said that right, wrote a pulsating nova is a bossa nova. And that is just a fabulous play on words.
That's awesome.
Kudos.
Let's see. One thing, this was sort of funny. Paul, I was watching a video with Paul, Dr. Paul Sutter, and he was saying, we were talking about metals, metal rich, things like that astronomers only see three elements in the universe.
Hydrogen, helium, everything.
And metal. Yeah.
Yeah.
So, if it's any heavier than helium, it's all just the same stuff, not hydrogen and helium.
So I have to give a shout out to the folks who are doing the chat that are down below us. This is the Weekly Space Hangout crew, and they are currently in the process of scheming fabulous things for our 500th anniversary. So if you are interested in scheming along, consider joining the Weekly Space Hangout at wshcrew.space.
There you go. Arnstro asks, do some planets have a North Pole? How about an equator? Bonus points for how many of other planets have tropics of Capricorn, Cancer, and Arctic circles.
So we can define all of these things on any object. And now I'm going to use, why don't I ever keep actual spheres where I can reach them? Yeah. Is that a sphere? Yes, I have actual spheres.
You can, though, reach and find spheres nearby.
I found one.
All right. That's a good sphere. Yeah.
Yes, it is labeled Jupiter.
Fun source.
So grab yourself a sphere that has lines on it so you can figure out how it's rotating. So the way they figure out which end is north and which end is south is you look at how it's rotating and you use the right-hand rule. So the way I'm rotating this is so that the direction of the rotation goes in the direction of my fingers on my right hand. My thumb is up. And if it's rotating in the direction of your fingers, then your thumb through its pole defines the North Pole. If you are pretending to be a planet, put your hand over your heart, turn in the direction your fingers are pointing, and your head is the North Pole and your feet are the South Pole. So as long as with the right-hand rule, your fingers are curling in the direction of rotation with your thumb as the pole, thumb is the North Pole, put your hand over your heart, rotate in the direction of your hand, your head is the North Pole. So this means that when we look out across our solar system, we can figure out some of the worlds are upside down because their rotation direction is opposite of all of the right side up worlds. Now, things like the equator are simply defined as 90 degrees off of those two poles. So if you draw a line between the two poles, find the midpoint, and then cut through the midpoint. Everywhere you cut through the surface, as you create two fragments of a planet, everywhere you cut through the surface, that's where the equator is. Now, it gets messier to figure out where the tropics are because the tropics are defined as the most northern point and the most southern point where the sun will eventually be straight overhead. So, in a world like Uranus that occasionally points its north pole straight at the sun and its south pole straight at the sun, it has no tropics
Right.
because the sun can be straight overhead on a pole. But if you look at Mars, which has a slightly different tilt from us, but not a hugely different tilt from us, it's going to have tropics, which are defined as places north and south of its equator, where occasionally the sun, one day per year, is going to be straight overhead as it goes over the Mars tropics. And I have no idea what we call those.
The Tropic of... Oh, good question.
It's the northern tropic on Mars and the southern tropic on Mars, and I'm sure someone named them, and I don't know what that
I'm going
is.
to find out.
This is why we have Google.
Race you, everybody.
I'm not racing you because I would knock my coffee onto my keyboard, and I respect my coffee.
No, I don't see any names for them.
I'll have to ask someone down at the Lunar and Planetary Institute because I'm sure there is someone who does Martian cartography that knows these things.
Yeah. They have them, obviously, as you mentioned, but I
Yeah.
don't see anyone talking about them, so...
Other questions?
More questions. Paranor 001 says we should talk about Carl Sagan and Pale Blue Dot for episode 500. I think if the plans work out, we'll do some kind of live event for 500.
Yeah. So my dog is misbehaving. One moment, and I will be right back.
Okay. Go ahead. Hit me with any questions you've got. Go to me. Olaf Lindquist. Ask a question about last week's episode. You can ask a question about anything. Tropic of Aries is a name from Arjun. I like that one a lot. Just to give you all a warning, so you may know, and I posted my latest episode of The Guide to Space, which was all about the Gaia spacecraft, and we sent that out the door yesterday, and the new QA is coming out the door today, and it's got special guest Emily Lakdawalla from the Planetary Society talking about her new book. Pamela has demonstration spheres, and I have books. So the design and engineering of the Curiosity rover, which is awesome. And like the color inside, which is so great. Oh.
So the truth is, it is May the 4th, and we were asked to explain the physics of lightsabers.
I thought you said your dog was misbehaving.
Because he was trying to steal a lightsaber and reminded me we were doing this.
That was awesome.
So, do you have any questions that you would wish to ask Master Leia about?
How do they work?
Her? So they're a plasma weapon that uses magnetic fields to help confine the plasma, and they only supply enough energy to allow them to go out to a certain distance.
How can you constrain plasma in a cylinder?
It's simply a torus of magnetic field. It's the same principle of how the magnetic fields on the sun are able to confine the tubes of plasma. Now, the catch is we had to master the science of monopoles to be able to get a single pole so that it didn't have to connect somewhere else. It would have actually been much easier to build something that the opposite of what Darth Maul did is to have two handles with the plasma in between, although that seems like a far easier way to injure yourself. And the cool thing is, because each of us get to choose the specific crystals that we use to focus the plasma and focus our monopoles, each different kind of crystal, just like rubies, diamonds, and sapphires, are all just carbon crystals with different impurities. We're able to get these different colors by choosing crystals that have different impurities within them.
Okay.
May the 4th be with you.
Yeah, no kidding. I'm sure other people are going to have some. What stops the plasma from heating up the air around you to unreasonable temperatures?
Oh, it does. It is ionizing the air all around it. This is part of why you see, especially when it makes contact with something, sparks flying. It's the air getting ionized all around it.
Right. Sure, sure. It's all just gibberish. And this is the time when I was mentioning you have here we go. You have, spherical demonstration objects all around you, and I have books. So
It's
here's a
true.
great
I
book,
also have books.
Star Trek Technology, written by Ethan Siegel, all about the science of Star Trek, how warp drives and all that could be possible. So, and he just published that. Apparently, warp drives are probably, possible if we can make negative mass, and if we can make, and the only that's the key. But
Yeah.
maybe antimatter has anti-gravity, which means it might have negative mass properties. They still don't
You
know.
know, they've managed to build some helium atoms out, I want to say at Pennsylvania State. And as near as we can tell, that's just not a anti-gravity does not come at all with antimatter. And it seems like the physics of the universe
You don't
would be
know.
fundamentally
You
different.
don't know. You don't know. It's still It's
I'm
still
allowed to say it seems
seems
improbable.
improbable. I think it's
I
perfectly
can be
reasonable to
wrong.
say it seems improbable, but I think at this point, most particle physicists really are hopeful that it has anti-gravity uh, characteristics, because that would be awesome. Um,
And now I'm overheating.
That's okay. You only got to survive for another 10 minutes.
Well, I still have my t-shirt on. So.
Oh, there you go. Let's hit some more questions. How do I pronounce the one that's written in Hebrew? It said room temperature superconductors and turbulent plasma breakthrough. I'm sorry, you have to give me a pronunciation guide before I can add your comment.
Oh, I wonder if that's Karen or Yov. I'm going to drop it into Google and find out how to pronounce it.
That would be cool. Colin Jones says, outside mathematics, there is no evidence of condensed negative mass anywhere in the universe. Yes, that is the truth.
Hi, Jacob. His name is Jacob.
Oh, there you go.
So, what was Jacob's question? I got
Oh,
distracted Googling.
uh, there was a question earlier up, or an explanation. Awesome. Let's have some more questions. Something keeps going bong.
That may be another thing on your computer if you have Discord open or if you have Slack
Yeah,
open.
I don't.
Both of those do various. Well, no. If the other person who's listening to us,
Yeah.
if you're new to Discord, you're probably. It took me forever to figure out what on my computer was making that weird noise.
Discord, right?
Yeah,
Yeah.
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 It's a subtle noise, which I greatly appreciate now that I know what it is.
Does yeah. I how are you liking Discord?
I'm liking it enough that we're actually, because it has website integration, which Slack doesn't, that we're going to start using it with all of our CosmoQuest projects. So the weekly space hangout is a sacred space where they decide who has the keys to what. We're going to create a much more open space. All are welcome for CosmoQuest over on Discord and integrated in with our website.
Right.
That'll probably be happening in the next couple of weeks.
Francisco Juarez asks about mountain and terrain detection on neutron stars. Have you heard about this?
Surface features on neutron stars?
Yeah.
My brain stopped.
that,
No, I hadn't heard about that.
that potentially.
I need to go read
Yeah.
that.
Yeah.
I
Can you put a link to the paper?
Yeah.
Yeah. Michael Meyer wants to know, can you work out the variation in the luminosity of standard candles by measuring the spectrum?
The problem is you can only get high resolution spectra with nearby objects. So when you produce a spectrum, you're taking all of the light from the object and dividing it out into a rainbow. And as you divide it out into the rainbow, you can see the various places where light is either absorbed by elements or where there's extra light given off by elements. This is the emission lines, the absorption line, and the background continuum, that rainbow. Now, any of you have a prism know, if you create a rainbow and you put paper really nearby, you're going to get a small, bright, 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 bright rainbow. As you move the rainbow, as you move the paper further and further away, the rainbow gets bigger. You can start to see more finer gradations in the colors, but it also gets fainter. When we're trying to do high resolution spectroscopy, which means we actually take that rainbow of light and we spread it out the size of a room, essentially. We fold it up so it's a whole bunch of little pieces that unfolded are the size of a room. When we do that, things get dim fast. So high resolution spectroscopy can only be done on bright objects. For a while, when they were starting to discover planets this way, everything they were looking at, you could see with your eyeball. Like, no telescope required. You could go outside, see it with your eyeball. Now, unfortunately, supernovae that are far away start out faint. And as you make the rainbow bigger and bigger and bigger, you don't have enough photons to see what's going on. So we can only do detailed measurements of metallicity with nearby things. Now, we can get basic lines from distant objects. This allows us to measure the redshift, so we can see some of the particularly bright hydrogen lines. We can see, I don't remember which lines they use in supernovae, but there's particular lines we can use, and that's how we get their redshift. We just can't accurately measure all of their metallicities.
Arjun asks, will the stars that are well above the galactic plane ever get pulled down to where we are? How does the spiral shape ever take place anyway?
So the spiral shape comes from how everything comes together, and there's usually something else that you're gravitationally interacting with, which drives what's called a spiral density wave. We did an entire episode on this a million years ago, and that physics hasn't changed. So basically, as things come in, their angular momentum allows them to form a disk where they spiral and merge. And super flat galaxies, like we were talking about a couple weeks ago, where we were talking about galaxies that don't have supermassive black holes, they manage to consistently come together and keep all the angular momentum in a plane. With things that have this big spheroid of stars, that's from things merging in and having chaotic interactions that poof them out. Globular clusters or spheres for the exact same reason. You have binary systems that will interact with a third star and eject one in a random direction. It's from all of these gravitational interactions and conservation of angular momentum that you poof out the sphere. Now, you can also add energy to the main disk and thicken it up by creating more erratic orbits. This is why we have what we call the thick disk.
And so a lot of those stars that are out on those crazy orbits, they had some bad circumstance to put them out onto that orbit, and that's their new orbit. Unless they interact in some way with something new to bring them into a more normal orbit, they're
done.
They're done. Yeah,
they're happy.
And
they don't care.
Yeah, and you would think like it would have to be a very random event to put it into that normal orbit that's back in line with the rest of the stars in the disk. No, they're
remarkably little probability of something like that happening.
Yeah. Well, I think we've reached the end of the episode, so why don't we wrap things up? Do you have any place you want people to go and check out, see, do,
Yes,
nap?
yes. You are so much better at this than I am. So starting tomorrow morning at, maths, 7 a.m. Actually, I'll be starting at 6 a.m. Eastern, which is 3 a.m. Pacific. we're going to be doing live coverage of the InSight launch, either until it gets canceled due to weather, which
Right.
unfortunately is an 80%
Yeah,
probability right
they've got
now.
fog right now.
Well, and it's high level visibility that's also a concern.
Yeah.
So part of that live coverage is going to include a regular set of giveaways. We have a bunch of Funko Pops and related things, and I have magic wands, and we're going to be giving away things once an hour.
Whoa.
And I shouldn't be allowed to have magic wands because I use them like an angry high school band instructor. Um, so we're going to be giving away surprises every hour to people who've completed at least 15 images on Mars. We're out looking for craters, marking craters, talking science, live streaming, InSight, providing coverage, providing commentary. And we're currently planning 3 hours of coverage, which will take us through the final engine firings a little less than 6,000 seconds after launch. Clearly, if it's a delayed launch, they do have a 2 hour opening, a 2 hour window during which they can launch. We will keep going until they're done doing interesting things.
Right.
After that, I will keep going for up to no longer than 6 hours, as long as we're getting at least, I think I said 600 images an hour and 15 people participating. So it's on you to science me and to keep talking. This is the goal.
Perfect.
This
Keep
will
her
all be
awake.
on Twitch.
Yep.
Twitch.tv on CosmoQuest X is the station.
That sounds great. One quick announcement for me then, which is that on Monday I'm going to be doing my live QA show, and this week we've got John Michael Gaudier. So we had Isaac Arthur, we had Cody from Cody's Lab, and this week it's going to be John Michael Gaudier, and then I think next week we're going to have Paul Sutter, and then I think you're going to show up at some point. So it's going to be a lot of fun. All right, let's wrap things up. So, time for all the thankings. Thank you, Pamela. Thanks to the WSH crew. If you want to join this community, go to wshcrew.space. Thanks, everybody in the YouTube chat. We will.
And thank you, everyone who supports Patreon, because they let us pay Susie and Chad, and we like to pay Susie and Chad.
And thanks
so
to
check that out at patreon.com/Astronomy Cast. And thank you to all of our fabulous sponsors who help us keep things going.
Right on. All right. We'll see you all next week.